Good morning everyone. Last class I asked one question that if we have an object in one side of the convex lens, will it give us always a real image, inverted image, yes or no? So let's see how glass lenses are forming images. So if we come here, there is a glass lens. In this glass lens you can see this is the optical axis, this is called the optical axis, and rays are coming from all directions, and this is a lens system where all the rays are converged in one particular point. So if this is a point A, it is forming A prime, and same thing is happening from B. From all the direction rays are coming and it converged in one particular point in B prime, and it is forming the image. In this particular case I just want to add one small thing that even rays are coming from all points of this object. So if I just consider some rays are coming from this particular point, so rays will go through this lens and then they will all converge in one particular point. So multiple rays are coming here and all will converge. So when it is forming an image, so it can start, rays can come from any point of this object. Okay, so then it is forming this complete image. Then here one small question it is coming, how this glass lens can converge or diverge the electron beam. If we remember the school days physics, that we have lens system and there is a rays are coming, and this is in the ear normal condition. When rays are coming here, this glass lens is denser than normal ear, so the path length of this length it will change. Same can happen if there is any rays are coming, if this is the object, if we just consider any rays are coming here, that also change its path because this is the glass lens is the denser object than the normal ear. That refractive index will play a vital role. Then when it will come out this ray from again, it will just follow the normal path and it will converge. So that is basically happening for each and every case where if one ray is going here, that overall area of this lens is very small, so they don't have to travel that much through this lens. But if something is coming through the central part, they have to travel more through this. So this density of this lens is helping us how it will converge or diverge. Okay, so you understand how rays are going through the lens system and it will converge. So here we are showing a very basic glass lens. So whenever we will do a ray diagram, we cannot use this so many rays, how we are drawing this. So we cannot use this many rays to draw a normal ray diagram. So it will be very complicated if we put this many rays. So most of the time we will not use this kind of diagram, we mostly use this kind of diagram. So what do you have here? Here we have a glass lens and this is the center point of this glass lens, and then this is the object, where object this ray it will go through this optical axis which is mentioned at the axis, and then there will be other three ray, it will come from the top part of this object which will go through this lens. One ray it will go through the focal point, this is the focus point which will go through this and converged in particular this point. The same thing, this is the chip ray which will go, or it will call the main ray, it will go through the center part of the lens and converged in the same point. Here this is the ray which will be going through this lens and converged one particular point right here. So this particular ray is going through the focus point 2. So now in this particular case, if you look at, this is called the focal length. So focal length means the distance between the focus point and the lens. So this is called the another focal length, that is I am marking with f1. Now this is my object. So this is the distance between object and the lens, and that is called u. And this is the distance between lens and the image, and that is called v. So now you can see that B is forming the B prime here and A is forming the A prime here. So we are getting an image, and this image is inverted, and you can see the size of this image is almost same like the object. And if this is my first point, this is my first focus point, and this will be my second focus point. So there is a two focus points, so focus point 1 and then 2. The same thing is here. So you can see that in this particular case, object is forming an image. The image size and object size is almost same, and it is inverted, and it is in opposite side. So how do we determine the focal length? So focal length we can determine by 1 by f. Focal length we can determine by 1 by f equals to 1 by v minus 1 by u. Okay. So there is another very common formula, we should use it if it is required, that it is 1 by f equals to mu minus 1 multiplied by 1 by r1 minus 1 by r2. What is that 1 by r1 and 1 by r2? So if we have a lens, you can see this is a curvature, right? This is half of the lens. So if you just consider this is one glass plate, this is the another glass plate, this will be the radius of that one particular point. So this will be the r1 and this will be the r2. So here mu is the refractive index of that glass lens. So there is a two very basic formula we can use it, that is how to calculate that focal length. And here the sign is opposite, because here the right hand side we are always considering it is positive, and left hand side we are considering it is negative. Okay. Now if what I mentioned that it will form a same size, the image size and the object size will be same, then what is the point of using that lens, or is it always same? Let's take a look in the next slide. So if there is a parallel rays and if your image is in infinite distance, it will come and merge in one particular point. When we are measuring the focal length of any lens system, there we discuss that okay, sun is at infinite distance and rays are coming and parallel rays are coming and merging in one particular point, and that is our focal point, that is our focus point, that where all the rays are converged, right? So if rays are coming from infinite distance, we can get this f here. Now the question was, is my image size and object size will be always same? No, it is depending on the position of our object here. So you can see again, this is I am just using now focus point is the f. So I have 1f, 2f. So here you can see this is my object is beyond 2f distance. When object is beyond 2f distance, it will form an image here. That image will be in between f and 2f, and the image size will be smaller than the object size. Okay. Now if that we already discussed, that if we have an object at 2f distance, it will always form a same size of the image. It will be an inverted image, same size of the image, and it will form at 2f position. What about the mode that, okay, if I move that object, so in between 2f and f, if my object is staying in between 2f and f, it will give us an image which is forming after 2f distance, and the image size here, image size, this is size of the image, is much bigger than object. Okay, so this is the ideal scenario where we have a lens system, we have an object, and we are getting a bigger image. Now if we keep the object at f, then what will happen? You will not get any image, because it cannot form any image in this particular case, because image is going to form at infinite distance. If we just this is not possible to form an image, they cannot merge properly. So it may be a very magnified image, in same site it can form, but it will be a real image, and it will be not an inverted also. Now if we consider that my object is in between f and lens, so if my object is staying somewhere here, we can expect that this ray can go further and they can merge somewhere here, and they can give us an image here. If it is giving us an image here, that image will be larger image, it will be a virtual image, and it will be not an inverted. So one thing it is clear from our diagram, ray diagram, that it is not true that all the time that lens system is going to give us a inverted image and the image size will be same as the object. So there are many different possibilities are there. So those things are true for the glass lens, but the electromagnetic lens functions in a little bit different way. But this is a single lens system we discussed so far. What about, we want to discuss little bit about a compound system. That compound system, how that compound microscope is working. So here let's take a two lens system. So this is the axis and this is my object, and rays will go, if this is the focus point, rays will go something like that, and then rest of the ray will come merge together and it will give us an image somewhere here. It will give us an image. Now we need a second lens system. Now we have a second lens. In this second lens system, these rays are going like that, and then we have our eye somewhere here. This is our eye which is visualizing. So the compound microscope, this is always a two lens system, right? So this is our lens number 1 and this is our lens number 2, and this is our object and this is our image. So if we just consider this is A, B, so if this point is A and this point is B, it is forming an image. We can tell that this is A prime and this is B prime. Okay, but now for this particular lens, this is working as a object. When we are considering that red lens, so this is working as a object here. Okay, and that is forming an image somewhere. If we just do this diagram here, you can see it that it is forming a much magnified image here. So for the second lens, this is working as an object and this is giving us an image. So in this particular case, we can tell that A double prime, B double prime. So now if we want to calculate the magnification, as I mentioned that previously, that okay, if this is your 1 centimeter and if this is your 10 centimeter, so your magnification will be 10 centimeter divided by 1 centimeter. So magnification mag of lens 1, what it will come? It will be like A prime B prime divided by AB. Then magnification of lens 2, we are getting that A double prime B double prime by A prime by B prime. Okay. Now the second slide, last lecture, what I told, the total magnification will be magnification of objective lens multiplied by magnification of eyepiece or ocular lens. Here then if we just implement these things, what we are getting, the total magnification, if we just consider this is the objective lens and this is the eye, then we are getting a magnification like that A prime B prime by AB multiplied by A double prime B double prime by A prime by B prime. So this part will go, so finally it will stay that prime B prime by AB. So total magnification will be, this is your object size and this is your image size, final image size. So you can consider that final image size divided by actual object size, you will get the total magnification. Okay, so far we discussed lot about optical microscopy, that how we can use the optical microscopy and what is the glass lens, role of the glass lens, how they are converging, how they are diverging, what kind of images we are getting. So now let us look at the main radiation, what kind of radiation we are getting. So here, what is the disadvantage and advantage of visible light? As I discussed previously, that visible light is not very damaging. If it is damaging, it can damage everything. We cannot see anything. So visible light is very good for us, and our eye is a wonderful detector for the visible light, and it is easy to focus. We don't need anything, we just need a glass lens. But major problem is wavelength, because wavelength is playing a vital role for the resolution, resolving power, that lambda. So that we are going to discuss in next slide. Now it is coming X-ray. The small wavelength, it has a good penetration power, it can go inside, but the major problem is that we don't know how to focus this X-ray, and it is damaging the sample. Because if you remember, most of the time if there is a fracture, any bone fracture, we are using X-ray. When we are using X-ray, most of the body part, if our hand fracture happened, most of the body part covered by a very heavy metal lead, and then X-ray is passing through one particular region which is helping us to find out the fracture. So why we covered with that heavy metal? Because we want to protect rest of our body parts, because X-ray is very damaging. Next it is coming electron. The small wavelength, the picometer, can be focused, but it is damaging sample like X-ray and poor penetration power. Next it is coming that neutrons, that low sample damaging, small wavelength in picometer range, but we are not very sure how to produce and how to focus. So how we can generate the neutron radiation? If there is a two atom fused, so sometimes some X-ray neutron will go away from the center part of that atom. So that time it will generate some kind of radiation, but this is not very well studied system, that how we can produce, how we can focus, and how it is going to image. So the major part is this three, that visible light, X-ray, and the electrons. Okay, so next we want to discuss about the electromagnetic spectrum. What is that electromagnetic spectrum? If you look at this electromagnetic spectrum, you can see it that it has a different kind of wavelength. So different types of rays are coming to the earth from sun, and it has a different kind of wavelength. So those wavelength, if you consider, sometime 1000 meter wavelength is also there. So mostly that radio frequency, that is we are talking about FM. So those radio frequency is mostly wavelength is within the range of 10 meter to 1 meter range, and then after that it is coming the microwave. Microwave, it is generating lots of heat also, and the microwave, the wavelength is coming 10 centimeter to 1 centimeter range. After that it is coming the infrared, the far infrared, thermal infrared, near infrared. So infrared belongs to this wavelength, and the frequency is written somewhere here. You can see the frequency, this wave. So infrared belongs to 1 millimeter to almost 1 micrometer range, and after that the visible light it is coming. So as I mentioned, it will come in between 400 nanometer to 750 nanometer. After that UV, ultraviolet ray, it will come. So you can see gradually the wavelength is decreasing, and when wavelength is shorter and shorter, it will be lot of energy, it will be there, and it will be harmful, because we are all very familiar that ultraviolet ray is not good for our health. Lot of time we use ultraviolet ray to decontaminate our biological hood, and that is doing the DNA damage also. So when the wavelength is shorter, it can penetrate through our body, as well as it is damaging, and it has lot of energy. So now it is coming X-ray. I already discussed about the X-ray, and then later it is coming the gamma ray. Now question it is coming, where electron beam it will come, because we all know that electron has a wave-like property and electron has a particle-like property. If electron has a wave-like property, so electron should come somewhere here. So I talked about this couple of times, that electron is damaging. So definitely electron will come after visible light, and we are discussing about the light microscope. Mostly we are using the wavelength within this range. So if wavelength is a limiting factor, even whatever microscope we are using, light microscope we are using, we cannot reach certain resolution, because limiting factor is wavelength here. Okay, we want to discuss little bit more about this one, that how do we calculate the wavelength of an electron beam. Let us do that. So from the de Broglie's equation, we all know that wavelength lambda equals to h by p, where h is a Planck constant, p is momentum. So lambda is the wavelength. Okay. So in next equation, from de Broglie's equation, we are getting that one. So now we can replace that. Momentum means mass into velocity. So if we have h, we can replace these things by mv. So this is our equation 2. Now in electron microscope we are generating an electron and it is going through a voltage. There is a high voltage is there and it is going through that. So if electron is going through a voltage, there will be a potential. That potential, if you want to calculate, it will be EV. So here V is the voltage. And now this potential energy, it will be this potential energy EV, it will be equivalent to kinetic energy half mv square. Again, m is the mass and v is the velocity. Now from that equation 3 we can get it that v equals to 2 EV by m root. Okay. So this is my equation 4. Now I want to replace this v in equation 2. So this v, this particular v in equation 2, this particular v will be replaced by this v. So now if we just consider lambda equals to h m v h m 2 e capital V by m, and now it will come h by 2 e m v. So mass of the electron is fixed, charge of the electron is fixed, Planck constant is fixed. So what is the value of this Planck constant h? It will be 6.62 into 10 to the power minus 34 joule per second, and charge of the electron it will be 1.6 into 10 to the power minus 19 coulomb, and then mass of the electron it will be 9.1 into 10 to the power minus 31. So if you put all these values here, you will get it like that 6.62 into 10 to the power minus 34 and root of 1.6 into 10 to the power minus 19 into 9.1 into 10 to the power minus 31, and then V, you will get it simplified form, that will be 12.5 into 10 to the power minus 10 divided by root V. Okay. So you can see this lambda is inversely proportional with this voltage. So in electron microscope there is a different voltage, different types of high tension, means high voltage microscopes are there, which is accelerating the speed of the electron. So it is inversely proportional. So lambda will be smaller if voltage is much higher. So based on the previous discussion, what we have so far, we have lambda equals to h by 2 MeV, and then finally I told that lambda equals to that it come 12 into 5 into 12 into 5 into 10 to the power minus 10 by root V. Now this voltage is changing, so 100 kilovolt, these are the electron microscope is available. That electron microscope will get it 100 kilovolt, 120 kilovolt, 200 kilovolt and 300 kilovolt. So here generally in 100 kilovolt if we calculate, we'll get that 3.88 picometer the wavelength. If we have a 200 kilovolt, you will get it some 2.74 picometer, and if we have a 300 kilovolt, you will get 2.24 picometer. Roughly this value may change here and there a little bit. Now one more last point I want to add for today's class. So one important part we didn't consider here. What is that important part? Important part is that when there is an electron and it is traveling through a high voltage and its velocity is accelerating, in a 200 kilovolt microscope, if you measure, the electron reach almost 70% of the light velocity. At 200 kilovolt electron speed, it will be almost 70% of the light. So here relativistic effect is an important part that we cannot ignore. So modified formula, what we wrote here, that will be modified like that. Okay, lambda equals to h by root 2 m0 ev multiplied by 1 ev by 2 m c square. So this will be the final formula to calculate the wavelength of the light, and we can make things more complicated. At this moment, for our purposes, I think that is good enough. So now you know that electron beam is always coming in a picometer range. So if I just go back, definitely electron will come somewhere this particular region in between X-ray and gamma ray. So I'll stop my second lecture here. Thank you all for your attention, and next class we'll discuss more about this one, that okay, how wavelength is helping us for the determining the resolving power of any microscope. See you in the next class.